Students, do you have any questions? Muhammad? We have these properties that exist in M such that for each x in S, the absolute value of f of x is less than or equal m. This is L infinity. We can consider for any f in L infinity of S this norm S, uniform norm, okay, equal to the supremum of this set f of S such that S belong to S, okay? Please note that since F is bounded, there exists a real numbers M such that for any element in S we have this property, okay, by this assumption, so that all of this is less than or equal M, so that this is a bounded function. So the set f of S such that S belongs to S if F bounded subset of real numbers, real numbers, okay, subset of real numbers, and so the supremum of this set is a real numbers, because this is a bounded and non-empty subset of R, okay? This supremum is a real numbers, okay? And this is very important that we consider these functions every element of this is a bounded function, because we must consider the supremum of numbers, real numbers. Okay. It is easy to check that this is a known function. Okay, this is a known function. And we can check this easily, and we can write this for you, or you can consider this as an very easy exercise. Okay. Okay. The condition of norm is very easy. This is a norm from L infinity is a norm form. Let me write this in a new line. This from L infinity to R is a norm function. Okay, and it is very easy because we see that for any f in L infinity of f, this norm is non-negative. It is very because we define this norm by this equality. All of this is non-negative, so that the supremum is non-negative. Okay, the norm of f equal to this supremum. Okay, f of s such that s belong to s. All of this is non-negative real numbers, so that this supremum is non-negative. And also it is very trivial that if this norm equal to 0, then this supremum must be 0. This supremum must be 0. This supremum must be 0, so that all of this must be 0. For any s in S, this absolute value must be 0, because all of this is non-negative. Okay, and this shows that for any s, f of s must be 0, so that f is the constant function 0. Constant function 0. Okay, and also we can consider opposite rules. If f equal to 0, the norm of f equal to 0. And also for any element in L infinity and for any alpha in complex numbers alpha f is a bounded function on S again, and we have this equality, this norm equal to absolute value of alpha multiplied by this norm. These two are very easy since f is an element of L infinity. There exists a real number such as m such that for any s in S we have this inequality. Alpha fs is less than or equal alpha n, so that for any s in S alpha f of S is less than or equal this, and this shows that alpha f is an element of L infinity. Please note that alpha f of S equal to alpha of f of alpha multiplied by f of S. We define this operation for you in the previous session. Alpha f of x equal to alpha multiplied by f of x, okay? So that we have this properties. If f belongs to L infinity and alpha is a complex number, then alpha f belongs to L infinity again, and also we have this equality. This is very easy because alpha, the norm of alpha s equal to the supremum. The supremum of alpha f of S such that S belongs to S, and this is equal to supremum of alpha f of S such that S belongs to S, and this is equal to the supremum of absolute value of alpha f of S, S belongs to S, and this is equal to absolute value of alpha, this multiplied by this supremum f of S, S belongs to S, and we know that this is the norm of f, so that this is equal to this absolute value multiplied by this norm. So that we have this property, and also for any f and g in L infinity of S, we have triangle inequality. This is less than or equal this plus equal to this supremum of f plus g of s belong to s, and this, okay, thank you Muhammad, s belong to s. And we know that by triangle inequality in complex numbers, because we know that f of s and g of s are complex numbers, this is less than or equal this the supremum of this set, because all of these is less than or equal this, and we know that this is less than or equal the supremum of the first item plus the supremum of the second item. Okay, and the first one is the norm of f, so that we have this condition that this is a norm function. Okay, also trivially we see that it is trivial that L infinity is an algebra and the constant function one is a unit for L infinity. It is very trivial because for any f in L, for any f we see that 1 multiplied by f equal to f multiplied by 1 equal to f. It is very trivial because, for example, for any s in s, this of f equal to of s multiplied by f of s, and this is equal to 1 f of s. This is equal to f of s, so that 1 f equal to f, and also f multiplied by 1 constant function 1 equal to f. And finally, this is an algebra norm on L infinity, because for any F and G in L infinity, we have this property. This is less than or equal this norm multiplied by this norm. Because, for example, this norm is this supremum, okay? F of S, G of S, such that S belong to S. And this is less than or equal this supremum F of S multiplied by this norm S belong to S. This is very trivial because because for any S in S, absolute value of G of S is less than or equal the norm of G. It is very trivial because the norm of G is the supremum of all of these objects, okay? So that this is less than or equal these real numbers, and we can write this norm multiplied by this supremum of S such that S belong to S and equal to the norm of G multiplied by the norm of S. And also this norm is complete. This is easy too, so that we have these conditions. This is algebra, okay, unital bonus algebra. And as another example, dear students, do you have any questions? Okay. Welcome, Ali. Mr. Ali Shahmani, do you have my voice? Okay. And we have this example 2. Let X be a topological space. Any topological space. Dear students, do you have the definition of topological space? Do you understand the definition of topological space? Let me write this for you. هل تعرف تعريف التوبولوجيا؟ Yes or no? Okay. We have a topology on X. Example, let X and 2 be a topological space. Okay. And C of X be the algebra of all continuous function on X. So C of X equal to the set of all functions from X to C such that F is continuous. So all of these functions must be continuous. We know that if we have two topological space, we can define the continuous function between two topological space, and CB of X equal to the set of all F from X to C such that F is continuous and bounded. Boundedness, so that this is equal to the set of all F in C of X such that F is bounded. F is a bounded function. Okay. Now we can define the supremum norm on this space, similar to the previous example. Okay. This is an unital Banach algebra again for any F in CB of X. We define this norm equal to the supremum of F of X such that X belongs to X. Then CB of X and this norm is a unital Banach algebra. Please check algebra similar the previous example. Okay, we see that this is a norm function and also this is the Banach algebra norms, and this is a complete norm functions. So that we have this important example. The v of x and this norm, the supremum norm, is a unital Banach algebra. Let me write this for you. If Fn, for example, is a Cauchy sequence in CV of x, then for each epsilon there exists a natural number such as n, such that for any m and n greater or equal n, we have this property that this norm is less than epsilon. Okay, but we know that for any x in x, this is less than or equal this norm, because we know that this is the supremum of all elements of this by this form. Okay, this shows that for any x in x, this is a Cauchy sequence. This is a Cauchy sequence this is, I must write Fn and Fm. Okay, of Cauchy sequence. Okay, Fn minus Gn minus, Fn minus Fn. This is the definition of Cauchy sequence. Okay, Fn, and also this is Fn and Fm. So that Fn of x n from 1 up to the infinity is a Cauchy sequence. In complex numbers, but we know that C is complete, is a complete space. So this must be convergent in C. convergent in C. Let the limit of fn of x and tend to the infinity equal to f of x, because if we change this x, this sequence change and its limit change. This limit depend on this x, so that we write f of x. Then we have a function f from x to such that f is continuous. It is very trivial, and you can see the continuity of this function in many books. Okay, it is very easy. And also f is a function. And this is very trivial, because for example, if we consider epsilon equal to 1, epsilon equal to 1, okay? For this epsilon, there exists a real number such as n1, n1 for example, a natural number, sorry, such that if n be greater or equal n, then this norm is less than or equal or epsilon, and or epsilon equal to 1, so that this subtraction must be less than or equal 1. And we can consider one of these, such as is. And finally, the norm of f is less than or equal this norm plus 1, and this is finite, so that f is a bounded function. Okay? Please note that in any function in norm space, we have this useful property that this norm minus this norm is less than f minus g, because the norm of f equal to the norm of f minus g, all of this is by x now, plus g. Okay, this f equal to this, and this is less than or equal this known by triangle in that this norm minus this norm is less than or equal this. Similarly, the norm of g equal to the norm of g minus f plus f, and this is less than or equal this norm plus the norm of f, and so that the norm of g minus the norm of f is less than or equal this again. And this shows that the absolute value of this is less than this. And we use this inequality in this step, okay? Because this is less than this, okay? This norm minus this norm is less than or equal this norm. Okay, this is or s. So that any Cauchy sequence in CB of x is a complete norm, and this is a Banach space and Banach algebra, and this Banach algebra is a unital Banach algebra because the constant function 1 belongs to this space again. Please note that the constant function 1 is a continuous and bounded function from x. We know that any constant function is a continuous function. In all topological space, constant functions are continuous, and this is a constant function, and constant functions are bounded because the value of this function is less than or equal 1. This function is continuous and bounded, so that this is a unital Banach algebra. And also we have this. Please note that if we consider compact space, for example this space, CB equal to C, because in compact space any continuous function are bounded. Please note that. It is trivial that CB of x is a subset of C of x. This is the bounded continuous function. This is the space of continuous function only. And if X is compact, then CB of X equal to C of X, because if F belong to C of X and X is compact, then to C, X to C is continuous and X is compact. This shows that F is bounded. Any continuous function on a compact space is bounded, so that to CB of X, this F is continuous and bounded, and this shows that in this case C of X is a subset of CB of X, and so we have this equality. Please note that if F from X to Y is continuous and X is compact, then we know that F of X is compact, and we know that any compact set is bounded. F of X is bounded. Please note that F of X is the subset of C. F of X is bounded. Okay? Please note that F of X is a subset of, this is a subset of complex number. F of X is a subset of complex number. And we know that any compact subset of complex number must be bounded and must be closed. And by the Heine-Borel theorem, we know that we have the converse of this observation. Any bounded and continue and any bounded subset of complex number, any bounded and closed subset of complex numbers must be compact by the Heine-Borel theorem. But in this case, we only need this property, that since F is continuous and is compact, the image of X under F of X is a compact subset of complex numbers, and any compact subset of complex numbers is a bounded set, so that this is bounded, and so F must be bounded. Okay, and we have this example, and in this example we see, we consider this open disk, open unit disk, and the closure of D equal to the set of all Z such that absolute value of Z is less. Okay, now R of D bar equal to the set of all F in C D bar, continuous function on D bar, such that F is analytic on D, or F is derivative on all point in D. It is easy to check that this is a unitary Banach algebra again. Okay, A of D, or A of D bar, equal to the set of all F from D bar to complex numbers such that for all X in D, F is derivative at X. Derivative. Okay. The set of all analytic function on D. Then it is easy to check that algebra again. Okay, dear students, do you have any questions? Okay. It is enough to this session. We will continue in the next session, inshallah, tomorrow. For now, goodbye.